Well, good evening, everyone. Welcome to the second video in the homework portal series. Let me share my screen just a moment. Okay. So the question here reads as, metal girders are often used in buildings. Okay. Used in buildings that have been constructed to withstand earthquakes. Okay. To aid the design of these buildings, experiments are undertaken to measure how the natural frequency F of the horizontal oscillations of metal girders varies with the dimensions. Okay. Just a moment, I did not put on the timer. This question is for 11 marks. So let us try to finish this in 11 marks, 11 minutes. Okay, so that, right, okay, I'll put it over here. Right, now, in an experiment, F was measured for vertically supported girders of the same cross-sectional area, but with different heights. So what is he measuring? He is measuring the frequency for different heights over here. Okay, so this is the height h here. So as a result of this, so the metal girder will now start vibrating. See, when you put a metal over here, what can happen is, when you fix it to the ground surface, it can vibrate like this, right? So the frequency of vibration can increase with the height h or decrease with the height h. We need to look at what is exactly happening here. Okay, now let me go back to this. The graph shows the data for the plotted for this experiment. Uncertainties are not shown. Okay, what is happening here? When the height of the girder is 5 meters, the frequency is very high. When the height keeps on increasing, the frequency starts reducing. I think that is obvious, because when you keep on increasing the height, so it will stand on its own height weight, and as a result of it, it will not be able to oscillate so much. Okay, agreed. And draw a best fit line for the data. So draw a best fit line. So how do you draw a best fit line? You need to draw a best fit line like this. Start from here and see to it that it passes through all the points. So when you say best fit line, it doesn't mean that you should always draw a straight line. It can also be a curved path. So see to it that it touches all of them with a smooth curve. Smooth curve like this. Right. So this is your best fit line. Okay. So you should not join by segment to segment. It should be a smooth curve. Then it is hypothesized that frequency f is inversely proportional to the height h. As you observe, it is very clear to us that f is inversely proportional to 1 by h. Okay, but we need to verify. We cannot just directly say that. By choosing two well-separated points on the best fit line that you have drawn, in A, it shows that this hypothesis is incorrect. You need to show that this hypothesis is incorrect. So how do you know whether this relationship is a inversely proportional or not? If you go to my video, so you will be able to see this in something called as transformations. I think it's in the 5th video, the last video I mentioned. What test would you like to administer so that you come to know that, okay, something is belongs to this particular function? Okay, so look into that. So towards it, what we do is, let me take up this point. Let me take up this point. He says take 2 points. Let me take up this point, and let me take up one more point. This point here. Let me take up this point. So what is this value? It is in midway between 5 and 10, which is 7.5. Here 10 and 15, midway 12.5 here. What are the corresponding y values? The y value for this one is 10, and for this one it is how many boxes here? 1, 2, 3. It's in mid of the third box, second and third box, right? So here you see this is 20, 22, 24, 26, 28, 30. That means each box here will correspond to 2 units. So therefore it is 22, 24, 25. This value is 25 here. If I draw a line here, midway, this value will be 25 over here. So what is that we need? We need to prove that f into h is equal to a constant. If this is verified, definitely it's an inversely relationship, right? So now what is f here? 7.5. 7.5 into, okay, I'll do one thing. I'll write it here in this itself. So it's for 4 marks. First one is selection of points. For selection of points and getting their coordinates. Getting their coordinates properly. Getting their coordinates properly. This will carry 1 mark. The second one is find F1 H1. What is F1 H1? Let us look into the F1 H1. 7.5 into 25. Okay. So 25 is the frequency, 7.5 is the height. When you do this, what is the answer that you get? Let me take my calculator. Where is it? It's here. Okay. So let me take up this and find out what is this value. 7.5, 25, star 7.5 will give me 187.5. 187.5. Now let me take the other 2 points. What are the other 2 points? Other 2 points is here it is 12.5, there it is 10. So this should be F2H2. F2H2 is equal to 10 multiplied by 12.5, which should be equal to 125. Okay. So that's what we so here you get 1 point and here you get 1 point, totally 2 points for this one here. And thus we come to know that F1H1 is not equal to F2H2. Hence, F is not inversely proportional to H. Okay, so you can mention all this. This will give you 1 more point. Okay, if these were equal, definitely it is inversely proportional. Since they are not equal, it is not inversely proportional. Okay, so let us move on to the next problem. Another solution, that is the relationship between F and H, is of the form below, given as F equal to K by H square. The graph shows a plot of F against H square, 1 by H square. Okay, so F versus 1 by H square is given. The uncertainties in H square, 1 by H square, are too small to be shown. Draw a best fit line for the data that supports the relationship F equal to K by H square. The moment there is a scatter plot, always remember he is asking you to plot a line of best fit. So let us draw here. Now the question is, should I start from this point? Should I stop anywhere over here? And so on. So what you do is you choose the points in such a way, choose the line in such a way that it should pass through all the error bars. Which is the error bar? This is the error bar. Okay, this region, it should pass through any one of these points over here. So if I choose this one here, see, I'm not drawing, I'm just showing it over here. If I'm choosing it over here, it will pass through all of them. It might not pass here, and when it comes here, it may pass, it may not pass. I do not know. I should use a scale to determine this. Okay, and do we have a scale here? Let me try it out with a straight line thingy. That do I have it? No, I don't have. I go to annotate. I don't have a straight line drawing. Go. Okay. Now let me take up. I don't have anything like that. Okay, fine. Shape. I have a straight line here. Yeah, I have a straight line here. So what I will do is I'll start from here. Now, if I pass through this one, yes, of course, but it doesn't pass through that particular thing. So what I will do is I'll keep it here. The final point, I'll fix it over here. And then I'll choose, I don't have anything here. Shape, no, not shape. No. Or maybe I have to choose this one. No, I have to choose this. Mouse. Oh, it draws again here. Okay, select. I'll take this and see, it passes somewhere over here. Okay, so it is almost touching this here, right? So this line would be a better one, right? So we have drawn a line of best fit over here, and then what do we have? Okay, next, the uncertainties in the H bar square are too small to be shown. This has come out of it. Okay, let me fix this. It's not coming. Okay, fine. Anyway, determine using the graph the constant k. Using the graph the constant k, you need to fix it. So how do I fix the constant k? Now, what is given as here as f is equal to k by h square, right? So this is your y, this is your 1 by h square is x, and m is nothing but the slope. Okay, slope is nothing but k. I need to find out the slope here. Where do I find? I take 2 points over here. I can take, as said, I'll start from this 30 here. I'll select this point here, and 20, I'll select one more point somewhere over here. And then I will draw a triangle here. Right. This base is already known to me. I already fixed. This is 10 into 10 to the power of minus 3. And what is this here? Corresponding to this one, it will be this point, which will be 40, 46, I think, right? What is it? 40, 50. So this should be 46 here. And corresponding to this point, it is 30 here. So therefore, your slope will be equal to 46 minus 30, which is 16, divided by 10 into 10 to the power of minus 3, which should be 16 into 10 power minus 2, 10 square. 10 square unit is, what is unit here? Unit should be, what is this here? Frequency is in hertz, and divided by this one should be per meter square. Per meter square. So this should be 1600 hertz per meter square, right? Per meter square, the meter square here. So this should be your answer. Okay, let me go down here. Determine the value of constant K. We already done this. So this should be 1600 meters square hertz. This is what I got. And then the next one, state one reason why the results of this experiment could not be used to predict the natural frequency of oscillations for girders of height 50 meters. 50 meters. Why can't we use this for 50 meters and above? Now, let me go back to the first one. So here it says that it is equal to, this line also goes along with me. So I don't know how to cancel this. Okay, let it be. Okay, so here they have conducted this experiment only until 25 meters. Beyond 25 meters, they were not able to conduct it. Why? The reason is because, let us read the problem once again. It says it's a metal girder. Okay, it's a metal girder that you keep it for. See, now this question, you need to write it based on common sense. Okay, you keep it like this over here. This is your surface. As the height increases, the weight of this girder will also increase, right? Weight of the girder will also increase. And the weight of the girder increases, this becomes more unstable. So what can happen? It may not be very stiff, because you see, when something is oscillating like this, this should be a flexible one. How should this be? This should be going like this over here, and it could also be going like this over here. The amplitude will be much larger. But when this length becomes larger and larger, then what can happen? This can actually fall down like this. It will not be very stable. So you cannot do it for a height of 50 meters. Okay, you need to mention very clearly that as length increases, weight also increases. Weight also increases. This implies it will be unstable. Need to mention this. Okay. So thus we come to an end to this particular question. Okay.